Okay, hello and welcome back to Chemistry Talk. Today I'll be discussing kinetics, continuing our discussion, and last video we covered first order kinetics, so now I will cover second order kinetics, which is the second most common form of a reaction. So for A to go to products in the second order reaction, you have the rate constant times A squared. Now if we wanted to integrate this into the rate equation, which we use to solve for concentrations, we get this equation: 1 over the concentration at the specified time minus 1 over the initial concentration equals the rate constant times the time, where, like I said, the initial concentration of A is A sub 0. The molar concentration of A at the time is A sub T. K is the rate constant, and T is the time. So there's no logarithms involved in second order reactions, but you do have fractions. Just important to note the linear relationship in second order kinetics. If you wanted to find this relationship linearly, you would support it with time on the x-axis and 1 over the concentration at the time on the y-axis. And you could graph this and that would show your linear relationship. So just wanted to point that out. Once again, we do have a linear relationship here. Now, the half-life of second order reactions is different than the half-life of the first order reactions. If you remember, the half-life of the first order reactions would equal the ln of 2 over K. However, we cannot say that with a change in concentration, we will see a change in the rate constant for a second order reaction. So we can't assume that it's 2. So we have a new equation: the half-life of a second order reaction, time for half the sample to decompose, is 1 divided by the rate constant times the initial concentration of the substance. Alright, so here's a standard problem. Decomposition of nitrogen dioxide to nitrogen oxide and oxygen is second order. Gives us K in inverse seconds. It gives us the balance of the reaction. It asks us 3 parts. The initial concentration of nitrogen dioxide is 0.5 molar. How long would it take for 80% of it to react? What's the half-life of this reaction? And what percent reacts after 5 seconds? Okay, so let's get started. So first thing to note here is that in this problem we are actually solving for time. Now, if you recall the formula on the previous slide, the integrated rate equation for second order reactions is 1 over the concentration of A at the specified time plus 1 over the initial concentration. And we get that equals the rate constant, K, times time. So here we're actually solving for T, the time. How long would it take? So let's note up here what we're given, and then we can just manipulate the formula to get the time. So the initial concentration of NO2 that would equal the 0.5 molar. Now, the concentration of nitrogen dioxide at the specified time, well, how long would it take for 80% of it to react? Another way of saying that is that means 20% of it is left. So if we take the 0.5 molar and multiply it by 20%, or 20 over 100, we get what's left when 80% of it reacts. And we get that number to be 0.1 molar. So 80% of it reacts, 20% of it is left. We take 20% of the initial concentration, and these are our starting values here. So now we can plug this into the formula. So 1 over the the final concentration, 0.1 molar, minus, that should be a minus sign, by the way, minus 1 over the initial concentration, 0.5 molar, equals K, the rate constant, 0.7592 times time. And we're solving for time here. So when we manipulate that, we get that the time for 80% of this to react is 10.5 seconds. What is the half-life when the initial concentration is 0.5 molar? Well, the half-life of second-order reactions equals 1 over the rate constant times the initial concentration. And that would equal 1 over 0.7592 times 0.5 molar. So the time, or the half-life for half of the sample to react, is 2.63 seconds. So this is happening fairly quickly. This is half the sample will decompose in about a little more than 2.5 seconds. And that's seconds there. Correct that. So second order reactions tend to be a little bit easier with the math. As you can see, the first order does require that natural logarithm, so the second order, it's usually a bit easier, but there is one small problem that you'll run into, which I'll show you right here. So what percent reacts after 5 seconds if the initial concentration is 0.5 molar? Okay, so we have a multi-step problem here. We're looking for a percent, but before we can even do that, I need to find the final concentration of the nitrogen dioxide in this case. So the initial concentration is the same. It's that 0.5 molar. We represent that with that little sub-zero there. It's the initial 0.5 molar. The final concentration is what I need to find, and that's at the time t. That we'll call that x for now. We don't know. The time is 5 seconds, and the k is the same. It's the 0.7592. So the integrated rate equation for second order reactions is 1 over the concentration of the reactant at time t, in this case 5 seconds, minus 1 over the initial concentration equals KT. So now plugging in what we know, go back to blue here, plugging in what we know the initial concentration, but we're looking for x. So we have 1 over x minus 1 over 0.5 molar equals the k, 0.7592, times the time, 5 seconds. So we get that to equal 1 over x minus 2, whoops, that's messy, one over x minus 2 equals 3.796. Now to isolate the variable x, what we're looking for, I'm going to move the 2 over. So I get 1 over x equals 5.796. So this is the only algebraic problem you will run into with second order kinetics, is you have a x in the denominator here. Now, the easiest way to fix this is to just cross multiply the x to get it out of the denominator. So you would get 1 equals 5.796 x. And when you solve for x, this is the concentration at 5 seconds, you get 0.173 molar. So here we get 0.173 molar. That's what's left after 5 seconds. Now that's not what the question's asking. The question's asking what percent of it reacts. Well, we started off, change colors here. We started off with 0.5 molar. We have reacted and left 0.173 molar. So that means we have 0.327 molar left. And if we started off with 0.5 molar, I'm taking the part over the whole. The part is what we have left, the 0.327 molar, subtracting the concentration left from the initial, and we're dividing that by the starting point, and to get the percent, we multiply by 100. So we get the percent that's left after the reaction is complete is 65.4%. And that, in this case, is the final answer. So we found the concentration of nitrogen dioxide at 5 seconds. We did use the formula. Then to find the percent that reacts, I took our starting value, subtracted what was left in the end, and we got the 0.327 molar, divided that by what we started off with, and we got the percent that's left, 65.4%.